Now the best way to carry out this check is to check the scheme using the 11-step guide, and when a step is not applicable, you just ignore it. So let's carry out the 11-step check on this particular exercise. Step 1, design objectives. These are specified as life safety, in other words, to extract the smoke from the shop front using slot extraction to ensure smoke will not enter the reservoir. So that's step 1. Step 2, design fire size. In this, we have to determine the design fire size that's going to be adopted in the scheme. Now, we're told that it's standard response sprinklers are to be installed, and the convention for standard response sprinklers is using a 5 megawatt fire with an area of 9 square metres and a perimeter of 12 metres. This is the general design fire size for a building fitted with standard response sprinklers. So we know the design fire size. Let's now determine the mass flow rate of smoke coming out of the opening. Now there's 3 models available, and in this case we're going to use this model, which is from PD 7974. As you can see, it's a fairly simple model with only 3 variables. It's got QP, the convective heat output of the fire, WO, the width of the opening, and HO is the height of the opening. And this model is presented by the Technical Memorandum 19, 1995, and it's issued by the Chartered Institute of Building Surveying Engineers and in PD 7974 Part 2. So let's put in our known variables. Now we know the convective heat output is 5,000 kilowatts. Now we need to know the dimensions of the openings. Now in this case the width will be 12.2 metres and the height is 2.4 metres plus 0.5 as they are removing the downstand, which will make it 2.9 metres. So don't forget they're removing the downstand, so it'll make it 2.9 metres. Put in those variables, you'll have got a mass flow rate of smoke out the opening of 23.65 kilograms a second. That's the mass flow rate. Let's move on to step 4 now, determining the temperature of the smoke. And the formula to apply is as follows. Theta equals QP divided by MC, where theta is your temperature rise in degrees Kelvin. QP is the convective heat output in kilowatts. M is your mass flow rate of smoke in kilograms a second. And your C is your specific heat capacity. If you'd have put them in, you'd have got a theta value of 209 degrees Kelvin. This gives us a theta value of 209 degrees Kelvin. And this is the temperature increase. But now we need to actually work out what is the absolute average temperature of the smoke. And this is the formula you apply. TL equals TO plus theta, where TL is your absolute average temperature of the smoke, TO is your ambient, and plus theta is your temperature increase. This would give you a temperature of the smoke, an absolute average temperature of the smoke of 497 degrees Kelvin. Now this is a high temperature as what you would expect with a 5 megawatt fire leaving in the opening, as there is not much entrainment. Now this is not a problem though, because the temperature of the smoke will not affect tenability in the shop, because the shop should meet acceptable travel distances. There should be nobody in that shop by the time this has gone off. It's already met the travel distances. Do you understand? The tenability limit of 200 degrees C applies to the smoke below people who may be in the mall itself or elsewhere. In other words, where people are still in there trying to get out. The life safety is the shop, well, that's covered. They've met the travel distances. The main issue you've got to consider is that the ducting where the smoke is to be extracted from can withstand these high temperatures. So make sure any ducting, anywhere that smoke has got to travel, has got to be able to take that hot smoke, because it's extremely hot smoke. Now that covers step 4. Let's move on to step 5, which is your stratification check. Obviously, in this case, the smoke has been extracted as it leaves the shop, so there's no stratification check. You can ignore that. Move on to step 6, which is your ventilation requirements. Well, in this case, the ventilation requirements are simply to extract the smoke as it leaves the shop. Now, we know how much smoke is leaving, and it's 23.65 kilograms a second. Now, we need to convert this into a volumetric flow rate to work out what the volumetric flow rate is to be extracted, taking into account that the fact that the smoke will be very hot and it will have expanded quite considerably. And this is the formula to apply. V equals M divided by rho 0 times TL divided by your T theta. And if you'd have put in your known variables, you'd have worked out that you've actually got 34 metres cubed a second of hot smoke leaving the opening. So that's a volumetric flow of leaving the actual opening is 34 metres cubed a second. Now, to ensure that smoke does not pass over the vents in slot extraction, you've got to increase the volumetric flow rate by a factor of 2/3. In other words, you've got to multiply it by 1.67. This is making sure, it's a safety factor, to make sure the smoke does not get past the extraction. by the slot extraction. So you increase it by, multiply it by 1.67. What they're saying is, for safety, you should actually increase it to 56.8 cubic meters a second. So that is what the slot extraction rate should be, 56.8 meters cubed a second. So to summarise, the slot extraction rate proposed at 45 metres cubed a second is not adequate, and you would require it to be increased to 56.8 metres cubed a second, and make sure all the ducting is fire resistant to accept the temperatures expected. Now the rest of the 11-step guide in this particular circumstance is not relevant, so you've actually finished the exercise now. You needed to just work out, is the slot extraction rate okay? Well, it isn't, you will have to increase it. That completes this exercise.